Good afternoon all. My name is Paul Mackerras. I work for IBM in the Linux Technology Centre in a group based in Canberra, Australia. And we call ourselves AusLabs, that's why it says AusLabs there. And for the last 4 years or so, I and several other people have been working on making KVM work on IBM's power processors. And so today, what I'd like to tell you about is where we're up to with that, the product that we've developed that is now being distributed and sold, which is based on POWER8, and then talk about some of the issues that we've discovered have arisen in practice due to the intersection between how the power architecture works on the one hand and how KVM works on the other hand. So I'm not going to talk about in much detail the technical details of KVM on POWER8. I've covered that in previous talks at this forum and elsewhere. But what I'd like to start with is talking about the POWER8 systems that IBM released in April. And you can see there's 3 of them that have a Linux circle on them. And those 3 you can order with a KVM-based hypervisor on them, which you can use instead of IBM's proprietary PowerKVM. So for things like, a cloud application, you can get a system which will have a KVM hypervisor, which actually works just like KVM on x86, with a few minor little differences, which I'll talk about, and integrates into your management infrastructure much better than PowerKVM would. So this is actually a seismic shift for the Power brand in IBM. To be selling an open source KVM-based hypervisor as an alternative to their proprietary hypervisor is actually really massive. So this PowerKVM product that we call it, basically what it is, it's a host operating system. It's available as an optional preload on those IBM POWER8-based servers that I was talking about. On top of it, you can run Linux on Power guests. So we don't currently support any other operating systems other than Linux. But we do support both big endian and little endian guests. So the RHEL family from 6.5 and later, the SLES family, SP3, SLES 11 SP3 and later releases. And just recently, Ubuntu 14.04, 14.10 are supported. And of course, the community distributions such as Fedora and OpenSUSE. You can run any of those as guests. This host OS is open source. It's essentially based on Fedora 19. We have a 3.10.23 kernel with quite a lot of our own patches. QEMU 1.6 and libvirt 1.1.3 and Kimchi, which is it's an open source project that I think IBM started. It provides a graphical user interface for managing a small number of guests, and it sort of provides just a few clicks to provision a new guest and install an operating system. So for managing the guests, you either use Kimchi or you use something that uses libvirt. It's an open system. We haven't locked it down in any way. You can SSH in as root and you can change things, configure things. If you change things too extensively, then we might start to say that it's going to be hard to support that. But for normal things, that's fine. You just SSH in as root and configure it the way you want. You can install additional software if you've got cloud management agents, OpenStack, the overt, what was it, Rev agent, what do you call it? Yeah, and other things like that you can install. Or if you like, you can actually replace it completely by another distribution. And once we have the enterprise distributions supporting running on these machines in hypervisor mode and supporting guests, that will be quite a viable option. As I said, it's supported by IBM. I've spent actually probably 80% of the last year responding to bugs generated by the testing team, where they take great delight in taking a piece of software and just torturing it until it breaks. Then they hand you the pieces and say, fix it. So we've been fixing it. So from where we started to where we are at the release, we have fixed a lot of bugs. Each version, the standard IBM policy, supported for 3 years from its initial release. Current version is called version 2.1.0. That's the first release. Don't ask me why it was 2.1.0, but it is, and that will be supported then for 3 years from the 10th of June this year. And then we've had a couple of service packs since then. And then we've got a new version. Well, it's not a new version, it's an update. 2.1.1 should be out fairly soon now. The differences there is that supports PCI pass-through. So we have PCI pass-through based on VFIO. Once again, it's undergone extensive testing for a specific set of PCI adapters, and that's now supported. And it has an update to the kernel, QEMU up to 2.0 and libvirt. Next year we'll have a version 3.1, and being Fedora-based, you can either upgrade with Yum or you can reinstall with the new system. And of course, the attraction of using KVM is that you get very similar usage patterns and interfaces to what you get on an x86 machine, and so that makes it much easier to interoperate in an environment where you already have x86 KVM machines. There are some differences, of course, inside the guest. Because we support Linux on Power guests, we support the platform conventions of Linux on Power, so that, for instance, we have a device tree instead of having DMI data. So in your Linux on Power guest, you don't use DMI decode, you use LSHW or something like that. And there are some differences in virtual to physical CPU mappings, which I'll talk about later, that are some of the differences that people notice. I'll talk very briefly about Power8. This was released in June. Seems at this stage to be a really good performer. Up to 12 cores per chip. Each core can do 8 threads, so you get up to 96 threads of execution per chip. Superscalar, big caches. It also has on-chip accelerators, which are separate from the cores. The cores have a number of new features, in particular transactional memory. This is a feature where you can use a tbegin instruction and then do loads and stores and other operations, and those loads and stores are not visible to the rest of the system until you do a tend instruction to commit that transaction. And if in the intervening time any other thread has modified those parts of memory, those cache lines, then the transaction aborts and none of it is visible. So it enables you to do a kind of atomic update to memory of more than one word. You can do a large number of changes to memory as one atomic transaction. So the things that are relevant for KVM are firstly that we have now 8 threads per core. That's SMTS, that's simultaneous multi-threading. That's up from 4 threads per core in Power 7. The increase from 4 to 8 threads gives us a small performance improvement in some workloads. In other workloads, SMT4 actually performs just about as well as SMT8. The core automatically switches between modes, 1, 2, 4 or 8 threads being active. When you switch to a smaller number of threads being active, then each thread gets more of the resources of the core, so that as you go to higher modes, the resources of the core, to some degree, they're partitioned, but in any event, they're shared, and so each thread gets less resources, of course. Now, the critical thing, which is true in Power 7 as well, is that all the threads share the one MMU context. What that means is that they have to be in what I'll call a partition So that's the host counts as a partition and each guest counts as one partition. So all of the threads have to be in the same guest, or they all have to be in the host. You can't have some in the host with the MMU on and some in the guest. You can run hypervisor code with the MMU off, which we call real mode, and real mode hypervisor code can run concurrently with any partition. But the constraint is, of course, then you can access the linear mapping in the kernel data, but you can't access anything else. You can't access the vmalloc space, you can't access page structs, just the linear mapping. And that really restricts what code you can safely run. Now, a new thing in POWER8 is that you can split the core into 4 subcores. So then you have effectively 4 cores. You have 4 MMU contexts. And so you can run up to 4 guests on the one core. And then each of those subcores gets 2 threads. So each subcore can either run 1 thread or 2 threads. Now, the advantage is that that's relaxed the requirements about what you can run concurrently on the core. The disadvantage is that the core is then permanently in this SMT8 mode, where the resources are to some degree partitioned. In particular, each subcore gets 1 dispatch cycle out of 4, so that each subcore will run in single-threaded mode more slowly than the core itself would run in single-threaded mode. The reason they did that is because they were worried about the impact of one partition on another, that if you had one partition doing very heavy computation of some kind, it would affect the performance you see in another partition, and this is designed to make the performance more predictable. Now, what we've currently implemented is a single system-wide selection of that mode under the control of the system administrator. So you have just a single number, it's a file in sysfs. You can access it using the ppc64 CPU command, and you can set it to 1 or you can set it to 4, and that applies to every core in the system. In principle, it would be possible to have each core in a different mode, and I'll talk about that later. But this is what we've implemented so far. Other things that are new in POWER8, we have a fast IPI mechanism, which is, we've got this new instruction called message send. So that generates a message that goes across the fabric to another thread, and in that thread, if interrupts are enabled, you take an interrupt using a new interrupt vector, which is fine. There's also a variant available for supervisor mode code called message send P for privileged, and that has the constraint that you can only send the messages within the core. And the reason for that is that the hardware guys didn't see how to map a logical CPU number to a physical CPU number, which you need to do because the guest CPUs can move around on the physical CPUs. But still, supervisor mode code can use this within one core, and so thread 2 can send an IPI to thread 5, for instance. So how do you specify thread 5? Well, you have 5 in a register that is a parameter to the instruction. And how do you know what your own number is? There's a special purpose register that tells you it contains 2. Now, the thing is that neither of those numbers are virtualizable by the hypervisor. So this means that if you have a guest that knows that it's running in SMT8 mode, and if it's, say, Linux, it will think, I'm on POWER8, good, I can use this instruction to send an IPI. But that means that vCPU2 has to be on thread 2 and vCPU5 has to be on thread 5, because otherwise the IPI will go to the wrong place. So that's a nice feature for performance, but they didn't add the virtualization, so that becomes another constraint on how KVM can map virtual CPUs to physical CPUs. There's the micro-partition prefetch. This is quite nice, actually. We've implemented this, and it seems to give a performance increase on pretty much every situation of up to 20 or 30%. Basically, what it does is that when you switch away from a guest, you can ask the hardware, you the hypervisor, can ask the hardware to look through the level 2 cache, find the cache tags, the real addresses for each valid line in the level 2 cache, and write those addresses into a buffer in memory. Then you can run some other guest. When you want to come back and run that guest again, you can give the address of that buffer to the hardware, and the hardware will go and it will read the addresses from that buffer and prefetch those cache lines into the level 2 cache. So that then by the time you get into the guest, the cache state that it left with is largely established, ready for it to go again. So we've implemented this on the guest context switch, and we find it reduces the impact of moving a vCPU from one core to another. Obviously because we can prefetch the lines into the destination CPU's cache that were present on the source CPU. Finally, there's transactional memory that I talked about briefly before. The impact for KVM is that because a transaction can be aborted at any time, the CPU actually maintains 2 copies of every user-visible register. So all the general purpose registers, all the floating point registers, all the vector registers, special purpose registers such as the link register and the counter, the XCR and so forth. There's 2 copies of them. There's one copy we call the transactional state, which is what's active at the moment, and then there's the checkpointed state, which is the state of all those registers as they were at the tbegin instruction. So when we go to context switch a guest, if it's in the middle of a transaction, we now have 2 lots of state. We have to read out both the transactional state and put that in memory, and the checkpointed state and store that in memory.
Can you just abort the transaction?
Sorry?
Can you just abort the transaction?
The transaction does get aborted, but you still have to save both sets of state. And the reason is that there's not just transactional or normal state, there's also a suspended state. And in the suspended state, you're not transactional, but you still do have these 2 sets of state. And if you context switch something that's in suspended state, you do have to save both sets of state to go back to it. This is a difference from the Intel implementation in that the Intel implementation doesn't have the suspended state. But you can start a transaction, do some things, suspend, and then do something like a printf, and then resume the transaction and then complete it. In fact, a system call may well cause an abort, but you could write to a logging buffer, for instance. If you've got a transaction and you want to debug it, and to debug it, you write to a log buffer, but if the writing to the log buffer is transactional and then the transaction fails, you don't see the writes to the log buffer, right? So to debug it, what you can do is you can suspend, write your debugging information to a log buffer, resume, and then complete. Anyway, that's... So what I'd like to talk about now is the impact that we have from this requirement that all of the threads in a core or a subcore have to be in the same partition. So our current solution is really fairly simple. We put the host into single thread per core mode. So we only have one thread, one CPU from each core online. So in the whole core mode, we have CPUs 0, 8, 16, 24 online, and all the other ones offline. In the 4-way split core mode, it's the even-numbered CPUs are online, the odd-numbered ones are offline. Now, the ones that are offline, we put into a power saving state using the nap instruction. And what this means is, of course, from the host Linux scheduler's point of view, they're not there. They don't exist. You don't run anything on them. You just ignore them. However, we can wake them up inside the KVM code by sending an interrupt and arrange for them to run a guest vCPU. So the advantage of this is that when a vCPU task comes along, A vCPU task obviously being the task or thread, software thread. This gets confusing because you're talking about threads meaning software threads as in QEMU and threads meaning hardware threads in the CPU. So this is why I say vCPU task to indicate the software thread. When that does the IO-kernel vCPU run and wants to enter the guest, if it's running on the core, it has the core. It doesn't have to coordinate with any other CPU to obtain control of the whole core, because the host kernel is running single-threaded. When you're running, you have control of a whole core or a whole subcore. So that means that we can just go and enter the guest quickly without doing any synchronization or coordination with other CPUs. So that's good for performance. Then what we do when we want to run more than one vCPU in a core, for instance, we might have a guest that's running in SMT4 or SMT8 mode, so there might be 8 vCPUs that want to run on this one core. We arrange for one of the vCPU tasks to take responsibility for the whole core and for running all those other 7 vCPUs. So we call that the runner task. So the other 7 vCPU tasks, once they put themselves in a list and they know there's a runner, they just go to sleep. So from the point of view of the host scheduler, those other 7 vCPU tasks are sleeping. In fact, their vCPUs are running because the runner task will enter the guest and arrange for the other 7 threads to be woken up and to start executing the corresponding vCPUs. And here we have to be careful to distinguish between the vCPU and the vCPU task, because the vCPU task is asleep, but the vCPU is actually on a thread executing instructions. Another consequence of this constraint that we start with is that whenever one vCPU needs to come out of the guest and go into the host, either to the host kernel MMU-on code or into the QEMU code, yeah, it wasn't exactly what I was intending to demonstrate. Okay. It's one out, all out. When one of them needs to come out, all of them have to come out, because we can't switch to the host MMU context until all of those threads that we're executing in the guest have come out of the guest. Now, so you might have one of them that does a hypercall that needs to be handled in the host, so they all come out, then the other 7 can elect a new runner, and if they can find a CPU to run on, they can then immediately re-enter the guest. So it's perhaps not as bad as it might be, but that's what we have to do. So it's probably become clear by now that the disadvantage of this, while it actually works quite well and performs reasonably well in practice, is that because we've disconnected the execution of the guest vCPU from the vCPU task, there are a number of assumptions that people and pieces of software make that then get broken. So the accounting on the host side, for instance, represents a core level assessment of CPU usage rather than a thread level assessment. This leads to the total CPU time seeming to be lower on the host than it is on the guest, because on the guest you'll be counting the CPU time for every thread, but on the host you're only counting the CPU time for each core. So it can be up to 8 times, it can appear to be up to 8 times higher in the guest side than on the host side. But then on the other hand, the utilisation seems to be higher on the host than it is on the guest, in that if you have if you have 8 threads and each of them is busy 10% of the time, you think, oh, that's 10% utilisation. But then you look on the host and the CPU that's running those 8 threads could be 80% busy. And so it looks like 80% on one side and 10% on the other side. And people say, what's going on here? And the next 2 points are sort of the same thing, really. In one case, it's a piece of software that's thinking, I've got a machine here and it's got 20 online CPUs. I can run 20 vCPUs, or it's got 12 cores, therefore 12 online CPUs. Therefore, I can only run 12 vCPUs, whereas in fact you can run up to 96 if you use SMT8 mode. And similarly, users get confused about the same thing. They think it's got 20 cores. If I run 20 vCPUs, is that fully committed? And the answer is, well, it depends. If you're running single-threaded vCPUs, then it is fully committed. If you're running SMT4, then it's only a quarter committed. virsh vCPU info output also gets confusing. It doesn't show the guest SMT modes. It will tend to say vCPUs are asleep because their tasks are asleep when they're actually active. NUMA-D also doesn't know about this, thinks you need one online CPU per vCPU. CPU hot plug becomes confusing because you really need to add, if you're in SMT8 mode, you should really add 8 more vCPUs to get 1 more core's worth of execution. And if you just add 1 vCPU to a guest that's in SMT8 mode, what does that mean? Does it mean that they get 1 more core and it's in single-thread mode? Or do we just say you can't do that? Or do we just say yes, but not actually start that vCPU until there's 8 to give to the guest? It's not entirely clear what to do there. We also find that if you pin a vCPU task to a single CPU, that can cause performance problems. And that's because, well, particularly if you pin multiple vCPUs that are all threads to the same CPU, then you get competition between ones that need to execute in the host and ones that want to execute in the guest, and they can't both do that at the same time if they're pinned to the same physical CPU. How am I going for time? 3 minutes. Okay. How could we solve this? Well, it would be nice to run the host in SMT8 mode, but then we have the problem that when we want to run a thread, we want to run a vCPU, we somehow have to get to control the other 7 threads, and they could be running anything. So perhaps we can do something with a high-priority kernel thread on each CPU. We will incur a hit of something like 10 microseconds to wake up that thread and have it tell us, yes, I've got the CPU now. But this is something we want to prototype and see if it will work. And then together with that, use a dynamic split core mode that would enable us to dynamically select whether to use whole core mode or four-way split mode, depending on what we want to run on the core at the time. The advantage would be that all the things on the previous slide would mostly go away. All of the assumptions about a host CPU equals a vCPU would now be true. It does look like it would be very complex, and it would probably not perform as well as what we have at the moment. Then a related thing that we have is the guest SMT modes, and this relates to the threads equals n parameter in libvirt and on the QEMU command line. What we do at the moment is that we say, for instance, if it's SMT4, we say the first 4 vCPUs are 1 virtual core and they will always run together, and the next 4 are another virtual core and they will always run together. And the advantage of that is that guests can control their own SMT mode. Virtual siblings are actually physical siblings. You can do cache-aware scheduling, and guests can control their own SMT mode. So that's all nice. The disadvantage of this is that the default is threads equals 1, which is usually not what people mean. So if they don't say threads equals 8 or threads equals 4 or something, they end up using a lot more of the machine than they really expect or need to, because mostly people expect a vCPU to be just a thread, not a whole core. So my alternate proposal, which we're going to try out, is to say that if we're saying threads equals 1, that's a sort of naive mode. And what we'll do then is that we'll just find a vCPU, for a vCPU that wants to run, we'll just find a core somewhere. And so you could have one core, one physical core, running any set of up to 8 vCPUs from the same guest. So you could get, vCPU 1, 17, 29, and 55 running on the same core. But if you say threads equals 2, 4, or 8, then you know what you're doing, and we'll just do what we did before. So that's my proposal. We'll try that out. I'd be interested to hear any reactions to how people think that might work or not work. And finally, the future work is to look at these things that I've talked about, to reduce the differences versus x86. We're going to do a little Indian host operating system, improve performance, etc. Questions? Yeah?
It's really complicating the CPU architecture, right? With these on-demand, enabling SMT, scaling, switching to different options.
Yeah.
Where is this coming from, this idea?
It's coming from basically the requirements of PowerVM, in that Power8 was obviously designed probably up to 4 to 5 years ago, and at that stage KVM wasn't really considered as something that was strategic. So, at this point we're working with the hardware that we have. PowerVM schedules things by cores. That's just the way it works. And so PowerVM has no particular need to have threads in different partitions. And because having threads in different partitions would actually take more hardware, more transistors, the designers didn't do it. I mean, they did it to a small extent with the 4-way split mode, in that they did then add 4 MMU contexts rather than just 1. And that gets us a certain distance. Yeah?
This may be probably a long discussion now, but I wonder if we could just treat the threads equals 1 problem as just as a user interface problem. I mean, you could let the user ask for 8 threads, but then you would just need to create just a few vCPU threads inside thread, so you can have 1 vCPU thread per CPU instead of exposing and confusing data to you. Just adjust the user interface so it matches the expectations. But
That's so that QEMU would default to threads equals 8. I think that was suggested at one point, and I think there was a objection to it, in that it would be a difference in behaviour between Power and x86. It would largely solve our problem.
I mean, the number of vCPU threads inside KVM, inside the kernel code, is just an implementation detail, right?
Well, it's argued, yes, you could argue that since the threads equals n on x86 basically affects nothing, that we could make it do on Power pretty much what we like. That's true. Any reaction from QEMU people?
Well, it cannot get worse than this, I think.
Sorry?
It cannot get worse than what you have now.
To some degree, that's true, yes.
You can easily do defaults per CPU type. So Power8 virtual CPU gets you 8 threads, Power 7 virtual CPU gets you 7 by default. I think we had
Sounds perfect.
We had a thread about this half a year ago, and that was one of the ideas there. I don't fully
Okay. I wonder if the problem was more to do with libvirt and its defaults, because it's possible that libvirt explicitly says threads equals something in every case. So it would be more a question of libvirt defaulting to threads equals 8 than QEMU. I believe that's timer, yeah.